Hi, I'm Whitney Espich, the CEO of the MIT Alumni Association, and I hope you enjoy this digital production created for alumni and friends like you.
Pleased to be here. Thanks for your attention. I think this is a really interesting topic discussion. What I'm planning to do in about 27 slides here is keep you from having to read a 300-page Academy's report on ocean CDR, carbon dioxide removal. I think, at least from my opinion, we are in a climate crisis and we need to be looking at immediate reductions in greenhouse gases that got us here, but in addition, ways to remove what we already have released and will release. So I'm going to go through slides that came out of this year-and-a-half activity and a report that's just over a couple months old now that summarizes that, and it's very much ocean-based. I also want to say before we get too far, I mean, when I think of responsible CDR, carbon dioxide removal, I mean, the whole goal is to reduce suffering and loss due to climate change. If we can't get to that goal, we shouldn't be thinking about altering the oceans and how they're functioning, but we already are doing that, right? We've already made changes and the oceans are suffering in the sense of changes in terms of temperature, in terms of sea level rise, in terms of oxygen, coastal nutrient loading. We've been doing fisheries for many centuries, so we've been making changes, and this is looking now at our ocean and our future. And I'll have a couple slides to introduce the dilemma we're in and why the ocean should be considered in terms of our response to the climate dilemma that we have us in. So that's my little bit of introduction. And again, you heard I'm from Woods Hole Oceanographic Institution, a not-for-profit research institution outside of Boston. So just two slides, and some of you may know these very well, others they might be new, but if you kind of look at our greenhouse gas emissions in terms of gigatons, billions of tons of CO2 emitted per year, we're on these various trajectories, business as usual. And what we've been coming to grips with, we being the community and things codified by like the Paris Accord, groups like the IPCC, is what would it take to keep our alteration of climate below 2 degrees? That's the red line here. And the first thing, when you look at the time scale on the bottom, we need to start immediately reducing our emission of greenhouse gases. And we can do this by switching over to non-CO2 sources of energy, things like solar, nuclear, wind. And we can cause them to go down, but they're never going to go, that's kind of the light brown here, to zero necessarily, because of things like, say, long-range air transportation. We're going to want to be using jet fuel to move cargo and people long distances. And there are other greenhouse gases contributing, but we're on a path that at best needs to include this blue area here, a removal of greenhouse gas, in this case, negative CO2 emissions from the atmosphere on the scale. When we look at these billions of tons, we're emitting about 40-something, 30-something for CO2 and close to 50 for all greenhouse gases right now. We need to start removing tens of billions of tons of CO2 per year through processes, and they can be land or ocean-based. And I'm here to talk about the ocean-based ways we might contribute to this reduction to bring us down to net zero, to keep to something like a 2-degree temperature curve. So it's a combination of things. It's not just, there's nothing I'm going to tell you today that says we can get there alone with net negative emissions or CDR, carbon dioxide removal. We're going to need both, and we're going to need research to get us with enough information to make the right choices to move down on this blue area here and increase its size. So that's kind of the biggest scale. So the next question is, well, why the oceans? Most of it you hear about direct air capture on land. We can engineer systems out of smokestacks or just out of the atmosphere to move CO2. Well, the ocean's sitting over here with this big circle with about 50 times more inorganic dissolved carbon than, say, other reservoirs, and already taking up about 1/3 of our greenhouse gases. So yes, we can do things on land, but there's often competition too on land with things like food supply. We can only grow trees or sequester carbon at competition with where people live and where we grow food. The ocean is larger and it has the biggest reservoirs. So it makes no sense, I think, to me, to not consider the ocean as part of our approach, our tools that we develop for reducing atmospheric CO2. And that's what nature does already for us. So we're hoping to increase some of these reservoir storage, long-term, durable storage, maybe not as permanent as a deep Earth reservoir of carbon, but certainly something that gives us 100 or more years of durability for carbon. And then as background on the academies, they did a report in 2015 on the need for CDR, carbon dioxide removal, making the case. And then by 2019, we're looking primarily on land-based technologies for removal of carbon from the atmosphere, CO2. It did include blue carbon, so we largely did not look at things like mangrove swamps and salt marshes. We're going to be talking mostly about open ocean and further away from the coastlines. So we were tasked to come up with an assessment of the benefits, risks, scales over which we could use the ocean for enhancing its ability to remove carbon dioxide. We were also asked to define the research R&D components and estimate some of the cost and potential impacts of those programs and come up with a way to implement them. I don't have enough time to go into detail on any one technology, but on the next slide, I'll talk about who funded us. But basically, we have a task that included 6 specific technologies that we were asked to look at. One, seaweed cultivation, growing macroalgae and removing some of that carbon. So this is photosynthesis, getting CO2 into plants, now growing in the ocean and getting that down deep enough to be sequestered, this durability long-term. I've worked mostly on nutrient fertilization, the ship here, putting something like iron in the ocean. We can talk about why iron, but I think it's enough to know that the ocean production, the uptake of CO2 from the atmosphere by the marine phytoplankton, the plants, is limited by nutrients. In particular, iron comes from dust from land, is one of the most limiting nutrients and essential to growth of these plants, which then by growing take up the CO2 and by their pathway through the food web and dying sink down deep enough to cause sequestration. So we're going to talk about that. We'll talk about ecosystem recovery a little bit. That's the idea away from the shoreline. What happens if we had more whales, if we had more conservation areas? Would that alone sequester, lock up more carbon? We have here something about artificial upwelling and downwelling. Deep waters have more of these essential nutrients than the shallow waters where the plants have grown and taken them up. So can you bring up some of that nutrient-rich water and create a bloom? We'll talk about that a little bit. You'd also have to bring back down the carbon dioxide that comes with that. So these are more engineered. You'd need large pipes, several 100 meters deep, 1,000 feet or more. But that is one of the 6 technologies. Ocean alkalinity, I'll get into because that's a chemical technique. This doesn't rely necessarily on the biology, growing plants and photosynthesis, but changing the chemistry to enhance the air-sea gas exchange, because a lot of the CO2 that we've emitted gets into the ocean because we've enhanced what's in the atmosphere. So by equilibrium and exchange into the surface, we enhance the uptake, and some of that sinks deep in the ocean. And electrochemical, the 6th technology here, is more about using energy and electrolysis to do things either to chemically change the uptake rates or physically separate carbon dioxide that's injected somewhere in the ocean or on land. So we'll come back to these, but that's as brief as I can make it. And hopefully, in Q&A, if you have specific questions, we'll get to them. I'll focus on 3 and I'll tell you why in a second. But just to give you an overview of what we were asked to do, we had about a year and a half. Climate Works is a philanthropically funded foundation, many different sources of funding, things like I might get this wrong, but I think the Grantham Foundation, things like the Gates. There's other large funders, but many, they consolidate this. They work in many areas. One of 10 is CDR, carbon dioxide removal, and also ocean CDR. So they came to the Academy and said, we want to know more about the capacity of the oceans. And the Academy said, we'll do that for you. Typically, many of you might be familiar, these are sponsored by federal agencies, DOE, National Science Foundation, coming to the academies, but this was a little bit different. We had many workshops and meetings, all during COVID, if you think about this time frame. So this was all virtual, unfortunately, but we had many experts testifying in addition to our committee. We had our own closed meetings, often many hours, a half a day long. We reviewed the state of the science as it exists. We developed common assessments, and we wrote this report and sent it out for external review. So that's a process if you're familiar with. It was new to me. It's my first Academy's report. 12 names here. I'm not going to go through all of them. Scott Doney deserves a lot of credit. University of Virginia's chair of that committee. I knew him as a student at Woods Hole back in the day. We also had a range of people, from looking at governance, so legal issues, looking at social issues. So we had a range of expertise that was needed to create a report like this. And I'll go over that contents, I think, in the next slide. Yeah. 9 chapters, introducing some of the case, like those first couple of slides of why we even are considering CDR in the first place, and oceans. I'll get briefly into some issues that cross over all of these, right? How would we conduct this? How would we have a transparent third-party accounting for carbon removal in an ocean setting? It's a little more difficult and challenging sometimes than on land to account for where the carbon goes once we, say, grow seaweed in bulk or increase with nutrient fertilization. This chapter 3, the uptake of CO2 into biomass, into plankton. We looked, so each of these are kind of self-standing. So if you only care about seaweed, you can pick up chapter 5 and learn about that. So there's a little bit of overlap and we get to a synthesis, but in that sense, it's a little more digestible, but it's pretty meaty. So I'm going to try and get through a lot here in a short period of time. So cross-cutting issues, I think, are important and interesting maybe in the Q&A, because there's a legal landscape that we all have to deal with, both for experiments and for potentially moving ahead for large-scale regulations. Who controls those waters, particularly for what I think about in the open ocean? Who controls the ocean commons? Who allows this to happen? Who benefits financially, say, from that type of use? There's social dimensions to all of this. If you create an effect in one place in the ocean, you might have a negative consequence somewhere else. Who profits from that? There's environmental impacts that would be common to any of these, right? We have both intended impacts. If we're not changing the ocean, they're not working. They're not changing the ability to take up carbon. So there will be environmental impacts, some of which we intend, some of which we don't know. We have to certify that, and we have to have a policy that supports this. And this last word, code of conduct, really means as an academic group, we feel that this should be done in open and transparent ways so you can follow our research plans, look at our data, you can come to your own conclusions, but we think that's important moving ahead. These common assessment criteria, and I'll give examples of them on 3 of the approaches, but it's like, what do we know? How efficient is it? How durable? How big could it ever be? How would you know, the monitoring, that it worked? What are these barriers to doing this from the environment and social side, and how would you govern it? So I'll get right into those. And as I do that, I'll come back to these 6, and just by the size of the circle, point you to where we came to after the end of this year-plus process. Was the larger the circle, kind of the more confidence we felt that this might have a payoff. But we did reach a conclusion, you'll hear at the end, that all of these have some merit, but the fertilization and seaweed in terms of biotic approaches, have some advantages given we're letting Mother Nature, say, provide the energy, photosynthesis. Ecosystem restoration has some advantages, whether it's as effective or not. It's a little smaller because we don't see how it will remove as much carbon. And the alkalinity approach shown in this little cartoon, we think has merit as well, but that's more of a engineered approach. That takes a lot of mineral reagents. So I'm going to focus in on fertilization, mostly with iron, seaweed, and alkalinity, but we have information on all six. So what do we know? Let's talk about the first three. And so we have a chapter on each. So when we got to the fertilization, we talk about things like the confidence that we know that it will work. And that word means to us remove CO2 from the atmosphere into seawater. Will it be durable? So that relates in the oceans to how deep it gets. We have to get not just a bloom where there's sunlight, but that carbon to sink deep enough where it's sequestered, where it's removed for maybe more than 100 years was kind of our time frame. It's something used in land-based CDR for things like tree farms and other ways sequester carbon. More is better. Gigatons of carbon, we had to get to tens of gigatons to have an impact on that CO2 budget. So we're looking for things that can reach those scales, maybe more. We have to know something about the consequences. There is a history here. I'll point out that we've been thinking about iron in particular longer than the others. And so there's a history of concern, people thinking about the geoengineering and the moral hazard. I think some of this really has gone away as we now experience the consequences of doing nothing in the sense of forest fires, high temperatures, sea level rise, loss of glaciers. So I think some of that has changed in the last 20 years. And we need to think about co-benefits. It might be hard to account for this microscopic algal, the fate of this material as it sinks, but I think we can do that. And the cost, though, is quite cheap for this one because we're not building a factory. Seaweed, let's compare that. So those same criteria. Well, we have a little less confidence that it will work. Seaweed's been around for a long time, but mostly to produce food. How well will it work for carbon dioxide removal? The next step of seaweed would be to make that sure that sinks to the bottom. If it gets there, it is sequestered. The removal might be a little bit smaller, it depends. The environmental impacts, you're putting in large-scale monoculture. You're talking about to get to a gigaton scale, something the size well beyond coastal waters in the open ocean, the state of Ohio, many times the size of New England. And that leads to its own consequences of a large-scale agricultural impact to natural systems. But we might choose that that's worthwhile, but that is there with anything when you bring it to scale. The co-benefits are easier to identify, feeding people, maybe biofuels, but there are some concerns about damage if you start having even shading and things of the ocean because of this larger scale, and the cost goes up a bit. You have to build ways to have this in the open ocean in a secure and stable way. And then the third one, before we compare all of them, is alkalinity. That's a little bit easier to say it will work. If you change the chemistry of the ocean to enhance its uptake of CO2 via gas exchange, that's chemistry. We know temperature affects that, the types of minerals we put in, but that you can scale up pretty big very quickly, so greater than some of these other numbers. But we really don't know anything about the environmental risk. You're not putting in a pure chemical reagent like in my lab in Woods Hole. You're putting in ground up rock that brings all kinds of things with it. And you're doing a lot of mining. You're bringing in billions of tons of mineral to get 1 billion tons of carbon out of the atmosphere. So we have a lot of unknowns and social challenges about that scale of dumping. We probably know the least about this in terms of the effects. It'll be moderately challenging to know about air-sea gas exchange, and you'll start to increase the costs. So something you'll find in the report, if you care about all six, is you can put them side by side. Probably more important than this type of table is when each of these we have words about what we mean by medium, high, and low. but just thinking about like this knowledge base. We talk about nutrient fertilization. We know more about that than others because it's been around longer, seaweed and iron, and say the least about things like large-scale alkalinity changes. Durability, scalability, some of these are easier to determine. Environmental risk, if you think about ecosystems recovery, the whole point is to improve ocean ecosystems. So we think that's relatively low risk. So that's what these tables can help us with. And that is there for all six. And I'll just end this part by saying we also go into things about costs. Like I said, nutrient fertilization and ecosystem recovery might be on the lower end. Something like electrochemical methods, because of the energy costs, would probably be the most expensive in terms of deployment. But a lot of useful information there. I point you to that. I'll summarize by saying all of them have many commonalities in terms of lack of knowledge, these governance, how do you do things on these scales, even the research, just to get a permit to put out a large-scale seaweed farm is not easy. Making sure we can measure these intended consequences and the unintended ones. Be ready for that. Be ready with a society that is skeptical about people intentionally altering ecosystems. Making sure we can independently monitor and verify, and ultimately anyway, cost will matter. So before I get into the research programs, the overall recommendation was to make sure we have enough information to inform making those decisions. So have a research program in place, and we think it should happen soon. And I'll talk about that next. It probably should happen in parallel. We'll talk about that as well, because we're not picking winners and losers. At this group was not charged with that. But we did see a lot of differences in terms of what we know, and we need to have some way to improve that knowledge base and be doing that in kind of an unbiased way. We think the academic community has the wherewithal to make a lot of progress. And that could be funded, by the way, commercially or philanthropically or by agencies. And probably all of the above is where that's going to come from. That's what the last line is about. So the second part here, the research agenda to get us there, that common set of things, 10 years, what would we need to know that's common to all of them, that's foundational research? This isn't really the science that I do. This is more about policy regulations. Do we have even a way to ocean iron? I think I get into this, but the London Dumping Convention, the London Protocols, actually have been modified about 15 years ago to allow for research, but not allow for commercialization of carbon credits by using the ocean. So we need to be moving ahead on that. I think we want to codify how we would behave as a group pushing for this, because it takes just one or two bad apples, bad behavior could set back this whole research agenda. We need, again, have transparent ways to monitor and account for it, consider social, ethical issues, who benefits, policies to support that, and think of this as capacity. What would it take? It would take significant capacities. That's a 10-year kind of $100 million effort, mostly outside of what I would call STEM, but getting more into social sciences. The other costs, we're only going to look ahead about 5 years and come up pretty quickly to about $1 billion. Scaled, now we did not do a very careful cost analysis. I will be one of the first to admit. What we did is we took the 6 things and said, okay, Ken, you've been involved in experiments to add nutrients. What do those cost? How many would we need? And how many could we do in 5 years? And that's how we got to these numbers. These are not priorities. It might cost more to advance electrochemical techniques because we have to build essentially factories, things on very large scales that process a lot of seawater, put a lot of energy into the ocean, where some of these are cheaper to do. But there's a combination in here. But we're talking about things that 170, $200 million a year. That's about half of the National Science Foundation Ocean Sciences budget. I'm not saying that Ocean Sciences at NSF will even do this, but it's a scale that we see from philanthropy, we see from agencies, and we think would make great progress on kind of a 5 to 10 year time frame to get things done. Now, be aware that we also don't think, while we advocated, let's move ahead on 6 things at once. So there'll be showstoppers. There'll be a reason why we might not, after a couple of years, want to continue with one of these. That baseline work, I think, needs to start and maybe taper off while we move more in the science of alkalinity and iron and seaweed. But we have to realize we're not going to spend that every year, and new things are both going to come on the table, and there are things that we weren't even tasked to look at. The fate of, say, biochar. Could we intentionally create carbon on land and bury it in the ocean? And then you'd reach implementation out here sometime 10 years later, as we have the confidence that it's worth moving ahead. So we're not talking about setting the agenda for 10 years. The priorities, look at our time. I always speak a little too long, but I think we're getting pretty far along here. I want to go through the 3 different things we've talked about. For fertilization, particular iron, it's things that you might imagine, the efficiency, how well can we add what it turns out to be a relatively small amount of iron. 1 part iron gives you 1,000 parts of carbon sequestration. So how can we enhance that efficiency? How can we track that? And can we move the field experiments that I did 20 years ago to larger scales, still things that I think have no likelihood of being permanently detrimental to the ocean, but where we can track them over annual timescales. And I think we need 5 to 10 years to get there. So we have a set of priorities and budget to do that. Seaweed, we really need to take seaweed farming that is largely done on the coastline and move it into the open ocean and come up with technologies to do that. One thing that you might not appreciate, while seaweed, as a plant, it also needs its share of nutrients. And you get to a certain scale, and we're going to have to do this somewhere where we either add in our nutrients, or there's things like an ARPA-E program where they're trying to grow seaweed in the sunlight and then have it vertically move down into the water, deeper water where there's more nutrients, and bring it back up again. Or use one of my tubes that I showed you and bring up nutrients. So there's combinations of these that might be needed when you get to certain scales to feed these macroalgae what they need to grow. And of course, we have to convey that stuff deeper into the ocean at a minimal cost. There's a natural path by which this happens, sloughing off of pieces of a seaweed frond, say, but we need to enhance that. We need to know more about the fate. Then alkalinity, OAE, ocean alkalinity enhancement. I apologize, I should have spelled that out. But basically, we know that maybe the least, what happens when you just put that ground up mineral in seawater, which plants and animals grow the best. Many of these minerals take decades to dissolve and have an impact. Would they stay on the beach where you deploy them? Would you put them in a ship and spread them across the ocean? Well, that means grinding to the point where things are sinking out before they dissolve. There's a lot of work left to do on that. And so this slide is really to remind us that as scientists and academics, and mostly for the public, we get really excited right at the beginning of any idea as we move ahead in the research. And iron has gone through this cycle where people got pretty excited and said, well, wait a minute, we might cause some harm that we don't know about. We might not be as efficient. I think we're coming out of that. Where we end up, time will tell. Ocean alkalinity is here. People get very excited, but I don't think they've gone through that same cycle of what putting 1 billion tons of ground mineral would do to ocean ecosystems. Seaweed, maybe they're over the hump. There's a lot of enthusiasm for growing seaweed for lots of reasons, mostly food. I think the biofuel may not go very far, but there's reasons to do them. But make sure we're not stopping doing something like iron just because we know the most about it, compared to something where we're just learning the lessons. So a couple more slides, key takeaways. Emissions reduction is important, but not enough. Land is not enough. The oceans play a role. Currently, we need to keep them as part of that discussion. We have to understand, will it work? How much carbon dioxide will it get? And what are the consequences? And are any of these 6 and others feasible? To what degree? I think that needs to happen now. My biggest regret is that we stopped doing this work. I think mostly because of public pressures 15 years ago. We could talk about that in Q&A. I think this is a research agenda to help decision makers, maybe commercial efforts to decide if to go forward. It's not an endorsement of anyone. And so we need to think about technology, the policy, the social impacts, co-benefits, many things that go with something that would be scaled up for that. Yeah, that was my last key slide. I'm going to shut these down. I can go back to them so I can see your questions and we'll go from there. But thank you very much.
Well, I want to thank you very much for that really introduction to this whole topic of sequestration of carbon in the oceans. We just saw the opening of the largest plant to remove CO2 from the atmosphere in Iceland, and the cost for that right now, since it's not, at scale widely, it's right. This initial plant is $750 a ton, as opposed to numbers like $50 to $150 a ton. Because we're a small group, instead of reading the chat questions, I'm going to ask you all to just raise your hand and then ask your question. I wanted to know a little about the deeper ocean CO2 and methane clathrates, and what is the rate of heat transfer in the ocean, and are we at risk from those gasifying, Ken?
Yeah, this is obviously beyond our report. Certainly, there's a lot of greenhouse gas locked up in things like these clathrates, or if you think of the Arctic, also they're warming in the Arctic. So we have other things we're concerned about at the same time that could overwhelm. As we know, methane is a much stronger greenhouse gas than carbon dioxide. Along with what are the issues maybe more closely tied to what I talked about, when you remove carbon, say, in plant biomass, as it decays, production of nitrous oxide is another one, a more potent greenhouse gas. Most, when we looked at least, I'll talk to what I know the most, iron. We account for that. What we have to do is make sure we measure, and we did this 20 years ago, when we remove organic matter and sink it, how much other greenhouse gases are produced. Methane actually is another one, by the way, but nitrous oxide is a concern because it would last long enough to get out and bubble out into the atmosphere. That was about a 5% offset of the net effect of the greenhouse gas removal. So greenhouse gas to greenhouse gas, accounting for its higher potency, for example. So, we are aware of those types of things. It does make it more difficult, but I think at least it makes it more expensive, even, especially these early experiments. We might have to measure that really carefully for 5 or 10 years. But hopefully if we say, okay, it's a 5% effect, then we're going to come up with cheaper ways even than the numbers I gave you to do some of these things in the ocean, because we're not going to be monitoring everything that happens at that point of deployment. We're not there yet.
Okay. David Herman, you have a question?
I do. Thank you. Thank you very much, Claude. Ken, I don't know if you remember, I attended a conference you hosted back at Woods Hole. I think it was 2008, sort of in the wake of all what was going on with Planktos and Climos and those commercial iron fertilization firms that are going out there.
Yeah.
So I don't want to pick on you or any of your collaborators, but I do remember my takeaway from that conference, which is going on 14 years ago now, I think. There was a lot of caution, and people were saying, we need to be careful about delving into this. The times might not be ready yet, but at least people were advocating more research. Um, I think in the years that have gone by, I think we're just in a much more desperate situation now. And clearly the mood, the sentiment among, I think my take on it within the scientific community is much more willing to try these techniques. But my question is like, why aren't we further along? So again, I don't mean to pick on you and, people Cole and Scott Doney and everybody, but I would have thought by now we would have conducted a lot more research on this topic. And also, it doesn't seem like since I was working on the London Dumping Convention, it doesn't seem like a lot more work has been accomplished in the governance aspect of this issue. So I guess, I'm just looking for your feedback on that.
Yeah. Well, maybe we should start with the governance. I think in some ways iron's ahead of the others because we did have that push. So there is something under the London protocols, whether they're signed or not. It's actually very few countries have signed the agreement that would limit ocean iron to research scale experiments. But we have that. It basically involves environmental impact assessment. The others don't have that protocol. And I think that's part of this code of conduct. I think we could follow those, and that's how we would move forward. Why we didn't do work, there's really two sides. One is the funding dried up. We could not get agencies. DOE pulled out of their programs. NSF said, we're not doing energy, we do basic research. And the basic question we had was, what controls ocean productivity? We answered that, iron in these areas, and how quickly and other things. So the production side got answered pretty well, but not the CDR side of that. And no one else came forward. In fact, the second part of why we didn't get further is even my own academic partners were shooting at us in the foot and saying, how can you have the hubris to do this? We know every time we muck with Mother Nature, we're creating more problems. It was clear to me back then, and I'll invite this group for comment, but I would say, even if you were against doing this, let's get the science so you could limit it to some degree. Without the science, we also had at that time some pretty bad behavior from the commercial groups going out, putting in iron. Haida Gwaii is an example in 2012, a group called Oceanos that sold this idea that if you put in some iron, they could increase the salmon returns off British Columbia. That was done without a permit. It was done without making any measurements of enhanced salmon return. And so that added to this reputation of reckless ideas and crazy scientists turning the knobs on something they can't control. So I've tried to be a little more deliberate these days. Glad to have something like this report behind us. And now I'm kind of trying to organize a subgroup of about 30 or 40 of us who are on the phone on Monday of this week to say, let's say, okay, what are the research priorities? How would we behave moving forward? But it's astounding for me to see the amount of funding, venture capital, philanthropy, people really say we have to make a difference. Doing nothing is not an option. I'm hoping that translates to the public and my peers, but I think certainly it was a path where a lot of people would say, stay away from. We actually signed a MOU between 12 different institutions back 15 years ago that said the research is important. And we wanted our directors to sign off so we could hold that up to the public who's saying, don't do this anymore. So we got as far as our MOU, but never got funding, and just kind of all went back to maybe studying nature is too glib, but we also kept doing experiments on natural addition of iron in that case, and how efficient nature can be after volcanic eruptions or forest fires and taking that material, creating blooms and removing carbon. So that's kind of where the field in iron went, but it never even got off the ground for many of these other technologies.
Well, if I can interrupt a second, Ken, last year there was a huge natural experiment across the mid-Atlantic with one of the largest amounts of iron being blown off the Sahara. Were we able to study that? What have we learned from that?
The Atlantic is less iron limited, but what I can tell you, I was hoping you were going to be like plugging the Australian wildfires, 2019, 2020, released a huge amount of carbon and then soot that fell into the Southern Ocean. The productivity as seen from space and autonomous platforms went through the roof, the chlorophyll levels. And I can tell you with some certainty, at least the science that was done, that several 100 million tons of carbon left the surface ocean in response to that single wildfire event. We did not have in place ships and people to go do more than give you those numbers I had. I've been in contact with people looking at the recent volcanic eruption in Tonga, this Aleutian Islands event referred to 2008, 10 million of tons of carbon removed from the surface. All of these natural events are pretty important. I just don't have the exact answer for this Atlantic one, and that's partly because of where it was and that we have less of a limit on iron in that area.
Neil, you have a question?
Yeah, I do. So our group, in this past year, I think learned that the whole issue about climate change is at best unsettled, as we heard from Steve Koonin. We've seen in the last couple of years worldwide a great example of what is likely the law of unintended consequences with our pandemic. What were probably well-intentioned scientists actually looking how they're going to prevent and deal with the next pandemic, let a virus out of a laboratory and millions of people are dead. Why is it not hubris to think that we can, to use a polite term, mess with the oceans and bad things won't happen? What about the law of unintended consequences?
I would say right now, if you wanted to protect the ocean, we'd stop fishing, right? There's some pretty imperfect things we do because we want protein, so we fish. Now, fisheries without any regulations or any fisheries science, we would have overfished and stripped things. It's not a perfect science and we can go around it, but at least by having some baseline, we could do something on global scale like fisheries in some places in sustainable ways. I think climate will have to be treated the same way. We're going to find that it's not perfect. We're going to turn some knobs and we're going to just have effects that we're not happy with. But if we don't do anything, and I think climate is a problem that requires both reducing those greenhouse gases that are out there, and that's at the pipe, at the tailpipe basically, and trying to increase storage that occurs naturally. So why wouldn't you consider an ocean that is already being changed, moving towards an ocean that is more productive, taking up more carbon? I think there's no reason to think that doing nothing is a better option than exploring at least these other types of technologies. That's a global experiment that I'm not happy with that we're doing.
So you're suggesting then that we turn some knobs and see what happens?
And in its way that is not, it's reversible, right? Every time I go out and put out
necessarily, though. How do we know it's reversible? We couldn't get that virus back into the Wuhan lab.
I don't think there's any evidence that the experiments we've done have caused permanent harm. And I don't think that analogy is appropriate for ocean fertilization or alkalinity.
And Neil, we won't even get into the question of whether it was a lab accident or whether it was from nature. That's still
granted,
unsettled.
It's an open question. I agree.
Yeah, okay. Phil?
I have the simplest question, I think. I think I lost the thread. Maybe it's on the slide. Let's say all of these ocean techniques can work in parallel. And let's say that they all work as well as can be reasonably hoped. What percentage of the current human-caused emissions would that absorb? What would that take care of?
So a lot of these, we use the gigaton of carbon dioxide level, and all of them can get to that, all 6 of them. In fact, alkalinity can go beyond that because it just depends on how much ground up mineral you put in the ocean. So I start adding up these and I can get to my 10. I had to remove on that second slide where I get that blue curve, tens of gigatons per year. This is an annual number. So we can make a dent, whether we need land and ocean. They're certainly large enough. Another answer to that too, though, is if society starts saying we want this, there'll be carbon markets. And so people will probably move ahead with any one of these 6, even if it's only 1 million tons, because they can sell that for $10 a ton or $100 a ton and make a profit.
So, so what's the total? So it sounds like about 10 gigatons could be handled in the ocean. What's the total level of emissions right now for CO2?
About 38 in those units of CO2 gigatons per year.
So
So
about
we have
20,
to reduce.
so about 25% could be handled by the oceans in the best case with what we know now.
And I don't think we're ever going to get to the get out of jail free card. Could this get to 38 or 50? There's just, in the case of ocean, there's a limit on nutrients that are there besides iron.
Okay.
You might say, and someone else could argue that, well, with the electrochemical techniques, it would take, I'm going to be a little glib here, but one estimate that I was doing was about 1,000 nuclear power plants for electrochemical techniques to get to their 1 gigaton. So, if you had 10,000 nuclear power plants or fusion or something, unlimited energy, you can make that one bigger. So there are things that could happen that might shift this around. But that's often, direct air capture is another one. How big could you make direct air capture? I think we're probably best off in a scenario where we reduce the emission, because that's something we can do now with various techniques. And then you build in these wedges of remediation and removal. But yes, I think they are big enough to be looked at seriously.
The most optimistic statement I've heard of this, my friend Jin, who was MIT class of, I think, 94, at a party in Cambridge about 20 years ago, somebody told him that they were concerned about global warming, as it was called then. And he said, I don't know what the problem is. The Earth needs to last only 50 more years.
It's easy to be pessimistic, even, yeah.
Yeah. I'd like to just make a comment on that last point, is that, the current emissions are what they are today, but if we're able to finally turn them around and have them go down, this number ends up being significantly larger percentage over time. And that could be really, really significant. I've got a couple questions for you, Ken. Number one is I head up the Energy and Environment Program for the MIT Club in Northern California. And we've been doing a lot of events on energy and environment and getting more and more into climate change. And just last year, we featured David Keith talking about solar geoengineering. And so, I think about this topic, especially the ocean iron fertilization one. And I'm kind of wondering, because that seems to be farthest along in your mind. Is there, a presentation that could be, like 45 minutes long or whatever, that goes into much more detail on the history of this and how it works and what the potential is for the future and so on, and a person who would be knowledgeable enough to give it?
Yeah, I mean, I would point you right now to the chapter we wrote on it. That's not a presentation of 45 minutes, but we summarize some of what's been done, where it's been done, how we come to these conclusions. There are experts who, and I've given those, I've got a 6-slide talk that I'm giving to a group, Ocean Sciences meeting next week, on ocean iron fertilization. I think what I'm trying to do with a larger group is really build a consensus around the key 5 or 6 things that we would need to do first to convince ourselves, really, because if we're not convinced, then the world would be convinced, that we have a handle on those efficiencies. Will it work? To what degree? And then those ecological consequences that come with that, these intended ones, changing ocean ecosystems, and unintended harmful algal blooms, what you might expect that we looked for and didn't see. Why didn't we see them? Why do they happen? So, there are, so yes, and I think who talked earlier about being at the Woods Hole conference, some things haven't changed. We have a pretty digestible, like we call it Oceanus. It's about a 20, 30 page document about issues about economics, about impacts, about governance that we put together that we share around widely. I'm hoping we'll have a website that people can come to and listen to those types of talks, even if you can't get me at 5 o'clock on what is this, Wednesday, in February. But yeah, a lot of what we have to be doing too isn't just talking to academics, but the public, I think, in terms of the need for CDR. And what I firmly believe that, that's not a get out of jail free card. That's not the only thing we need to be doing, right? I think people have a tendency not to want to go in this direction because they say you're giving fossil fuel companies the license to keep emitting because, you're going to remove everything they emit. I don't think we're ever going to get there. And so be upfront, bring them on board. And that's a different type of 40-minute talk, right, than a group like this that has some science and engineering background. And that's urgent, as almost as important as the science we have ahead of us. Because I could launch an expedition tomorrow to study the biological carbon pump response to iron on the scale I think we need. Might take me 2 years to get the permits, but we know those next experiments that need to be done, and they need to be replicated and done in different locations. So to me, the science isn't holding me back as much as the social license, and then of course the funding. But the funding 2020, 2022, I meant to say, but the last couple of years anyway, we're really seeing a renewed interest in CDR on land that has kind of preceded what we could do in the ocean, which you really just don't want to ignore the ocean. And then more, if it doesn't take too far before you start reading it, if we start reducing the reservoir here and the land, it's going to affect the ocean. So those exchange pathways trigger feedbacks that we also need to know more about, or at least to consider when we look at effects.
Ken, could you talk about the biome, the total, carbon and living creatures in the ocean, and has that distribution changed? How is it out of balance from what from the historical record? I'm especially thinking about Prochlorococcus, say, or the mesopelagic ocean fish populations. Go ahead.
No, I'm in one program called the Ocean Twilight Zone, and there's an order of magnitude uncertainty about that mid-water mesopelagic biomass. So we really don't know that at all. As far as surface productivity, there's some areas where we're seeing declines. I'm mostly at the biological carbon pump, and I know how much carbon is in total production, 50 gigatons of, I'm going to go to carbon, not CO2 per year. Primary productivity is the scale. About 10 of that sinks out of the surface sunlit euphotic zone, and 1 gets me down to 1,000 meters. So I'm going from 50 to 10 to 1 billion tons of carbon in the natural system that moves carbon that ultimately came from photosynthesis deeper in the ocean. That was carbon. I've got to multiply by 4 to get the CO2, but we're talking about flows in the ocean that are as big as our annual emissions, say, if I want to scale it that way. Your biomass number, the only one I've looked at recently were whales. Someone's proposing that we have to increase and go back to the population of whales before humans, because whales, by their feeding, break up material, form feces that release iron that the krill feed on, that then the whales feed on. So it's this feedback loop, right? You create a bloom and they're like gardeners, and then they sink to the bottom. Well, there's not enough whale, even the pre-human whale population is more like 10 to 20 million tons, not billion tons, of carbon sequestration potential. That's a bit why that ecosystem restoration circle was smaller, is there's just not enough fish in the ocean or even plants to really on their own do everything, scale into the hundreds of millions. So that's around about, I should know that total biomass number, I don't, but those are some of the arrows in and around in the ocean that we're talking about tweaking. Some pretty big numbers. And by the way, for those, you may have heard that, biology doesn't matter. There's a group in the ocean that thinks, well, if you're bringing up nutrients and carbon, biology is just bringing that same amount back down, having no net effect. So my counter to that is I think we're changing ocean ecology in ways we can't even measure now. It's warmer out there, it's more acidic. We've certainly changed mixing of deep nutrient-rich waters into the surface water by this temperature stratification. So we are changing ecosystems, but we just have a hard time measuring that impact on the biological carbon pump. So as a scientist, if I could get to the end of my career, just even knowing, is it getting bigger or weaker, this natural carbon pump, that would be a big step forward, let alone trying to make it bigger on purpose.
So you're saying it could be that, for instance, we might have already made the ocean carbon much smaller, and that just increases the problem that we have.
Right, warming the ocean increases that solubility, and then the biological pump, if it's driven by nutrients coming up, there would be less nutrients to go back down and make blooms. But there's a whole ecosystem in between. If we grow different types of plankton that sink diatoms, that sink more efficiently, I can increase this biological pump through natural processes. So we've sat around, and most estimates are that the ocean will decrease in its capacity to store carbon through air-sea exchange and the biological carbon pump. But I think there are big errors or uncertainties around that, low levels of confidence.
The numbers that you have for, or the experiments for growing the kelp or other seaweeds, is that factored including fertilization, or are those studies without fertilization?
Well, the numbers, I was talking about just now, the billions of tons that sinks down deep, that's just the natural cycle. And so we're thinking, could you double that to 2 billion? Yes. Could we make it 10 million? No, there's just not enough nutrients in the ocean. And this is just using iron, right? Another way I look at your question, though, when we added those nutrients, most of them were very inefficiently taken up. That iron, most of it was not bioavailable. So 90% of what we added just sank out and had no effect. So a lot of the research moving forward, the R&D, would be, can we make a more bioavailable form of iron that lasts longer, that's taken up more readily in an organic form into the plankton. And by the way, the plankton to grow, it's like 1 part iron to 500,000 parts carbon. So they don't need very much iron to make a lot of growth happen when that's their limit. If that's the one thing they need the most, that's one reason it's on the table still as cheap and relatively effective. Alkalinity is 1-to-1 roughly, depending on what minerals you grind up for getting a ton of carbon out. You need a ton of ground up olivine, for example, in the ocean. So we do have these different efficiencies, some handle on them, from nature, from weathering in the case of studying alkalinity, to blooms, natural blooms in the case of iron, or seaweed. So the seaweed growth. The seaweed issue, I think, is more about how do you get it down deep without expending a lot of energy. I think of a bale of hay with a brick in the middle. I mean, is there something we can simply do that once it's grown that would be a farming mechanism? Because that could be quite efficient, though. Think of that. That could be a rocket ship to the bottom. That's pretty efficient.
Okay, Andy, you have a question?
Yeah, thanks, Claude. So Ken, you mentioned earlier, the annual CO2 emissions of around, 38 gigatons or whatever. It's my understanding that that's sort of what's added to the atmosphere. So sort of our totals, natural plus human influences minus our natural sequestrant systems. Do you have any sort of senses, or is there a clear consensus on how much CO2 is annually sequestered by the oceans as a natural process?
Yeah, that about a third of that, basically 25% to 30% goes naturally right now into the ocean. So that's the 38's easier to add up. That's the release number from adding up all the fossil fuel we burn, land use type of issues. So that's what we're putting in. Not all of that ends up in the atmosphere. About a third ends up in land-based reservoirs and a third in the ocean and the other third in the atmosphere in round numbers. And so that's happening right now. A big research question is, will that change? Someone asked me, will the ocean number be 10% in 20 years? That would be really bad. Then that temperature curve goes up faster. We're trying to, with these techniques, make that number bigger. So now that number is 50% of our emissions can get into the ocean, not just the 30% that we have right now.
So just a follow up to that. So, because I just want to make sure that I'm clear on my understanding. So as I've tracked sort of CO2 in the atmosphere over, sort of my lifetime, there's obviously been a consistent pattern going up. Have you seen that? And I'm just going to use the round numbers of a third, a third, a third. Have you seen that, ocean sequestration's been about 13 gigatons, land has been about 13 gigatons, and then ultimately the increase has simply been human influence. And so we're just going to go, it's still going to be in theory 13 or so ocean, in theory 13 or so land. And then over the period of time, as we continue to emit more CO2 in the atmosphere, as we emit more CO2, it'll just be a larger amount that goes into the atmosphere.
Yeah, to the first part, we've measured that increase in the ocean. That's this whole ocean acidification side.
Yep.
We measured the decrease in pH. So we're measuring that in different ways. So directly, we see that same curve in the atmosphere in the ocean surface water. As far as that's driven largely by that air-sea pump, the solubility of gases. So there is a tendency as the atmosphere goes up, we're kind of lucky, then you push more into the ocean. So instead of being 13 out 50 years, it's still 30% if the ocean were the same temperature and the same conditions. In the future, if that were 50, the ocean could still take 30% of that new number 50 because of this air-sea solubility. So you just create an equilibrium that pushes more in. So
I got you.
We're lucky there, but
we wouldn't have that with land mass though, as we continue to cut more and more trees down, as the peat continues to whatever, permafrost gets exposed. So our land mass sequestration, they're decreasing.
Yeah, Amazon forest is the classic example of that, right?
Yeah.
Our sinks on land, unless we do something, are also not going in the right direction. So some of that increase in the atmosphere gets steeper, not just because of what we put in each year, but because of how little goes, the changes in those reservoirs, land and ocean being the two we're tracking pretty closely.
I got you. So I'm then, if I'm using a narrative to try and help explain this to a layman's person, it's as you've described, the pump process associated with CO2 from deep to the surface levels. That's going to take a similar type effect because of just how big the oceans are, and we're warming them. But we're still putting so much CO2 in, it's still going to have a variable. We do have the ability to adjust the land mass, with regenerative agriculture, with tree planting, with all sorts of other things. And so what you're trying to share is that we have a way to increase the amount of CO2 the oceans can also do as well. Because when Claude mentioned Climeworks the other day, I mean, like, I'm very familiar what's happened in Iceland, et cetera, but it only sequesters 4,000 tons of CO2. Like, that's when we emit 160 million tons a day. 4,000 isn't a lot.
You need an awful lot of direct air capture and energy to run those. That's fossil free, which is hard to find right now anyway.
Yeah,
But
and you also need a geological system that exists in Iceland to be able to store it.
Right. And absolutely, you kind of think of the ocean of having these two pumps. One's driven by the air-sea exchange. We call that the solubility pump. And that's going to happen no matter what, but it could get more efficient if you do alkalinity methods, right? If you change the chemistry by adding in minerals to make it more soluble. So we have one way to do that. And then the biological side, those biotic things like seaweed and iron are more about enhancing the growth of plants which take up CO2 with sunlight and getting that deep enough and not necessarily permanent. I didn't show you maps, but the ocean sequestration is typically timescales of 100 to 1,000 years. Before that, deep water burps back out somewhere. So this isn't necessarily, unless you continue doing it, going to be the same as geological sequestration, which is longer timescales, but probably enough and quite helpful if we're trying to adapt to or decrease the severity of the temperature curve, the melting curve, the sea level rise curve. So it doesn't stop it in the same fashion. Someone mentioned SRM. I think I'm going to throw that back out at you. Solar radiation management. That might be quicker at changing temperature because you just put something that blocks sunlight, but it never gets rid of the problem of greenhouse gases that have been emitted or would build up while you do that. So David Keith and others who look at that have something to say. They have ideas, but I think that's, to me, not as good as or a solution that actually gets rid of the problem, which is the excess CO2, the greenhouse gases, methane that we're putting in the atmosphere.
Are you saying because if you block the sunlight, respiration becomes greater relative to photosynthesis, so you really don't have that much of a net effect?
Well, that's a secondary thing. That also would happen, right? Plant growth would decrease in a darker world in the oceans and on land. I'm thinking more that CO2 would build up to 1,000 or something, and you never change that by SRM. You continue to emit, you never sequester. So someday when you were to stop SRM or disrupt that with a war, or just, you would end up with this jolt of temperature rise that would be unmanageable by any society. So I think you go after the CO2 itself rather than the Band-Aid. And I think David Keith is arguing in some of his cohorts that SRM has a pretty useful function for that shorter term, 5, 10 years, 20 years, whatever it is as a Band-Aid, but that we would still want to reduce the cause of that, why we need it in the first place. But it never really solves the fundamental problem of having these excess greenhouse gases that have very long residence times, and some of them, and we've got to reduce that if we choose to, try and adapt. Even adapting, the faster we get there, I think I'll tell this group, the harder it will be for society to adapt, for people to move. Island nations being underwater, it's here. Boston is a good example. A foot of sea level rise in the Boston Globe was the discussion today by 2050. That's a big economic hit. Moving Navy bases away from the coastline is a big security threat. I mean, there's just lots of reasons why if we could slow down the pace, that alone, I think, would help.
Okay, Joe, I think you're next for your question.
Yeah. Hi, Ken. I emailed you earlier about tomorrow. Ginkgo Bioworks is sponsoring a webinar on the role of synthetic biology in climate action. And I've been interested in, I know it's called ocean fertilization. I refer to it as a prebiotic for the marine microbiome because I think it's wholly analogous. And I was wondering what you thought about the role of synthetic biology in the carbon dioxide removal by the ocean. Where should we be what should we be working on? Yeah.
Yeah, I mean, I have not thought about it very much at all. I've not heard much about it. I'm intrigued, so send me the time and invite. I don't know if I can fit it into what I already have scheduled, but it rings true in that what I want to have happen is not just grow more phytoplankton, but ones that are more efficiently take up CO2 with less nutrient demand and then sink very efficiently deep. So anything we can do to enhance that direction of the biological carbon problem, the better. Right now, the ocean's, ranges that efficiency from production to sequestration is, 50% or more in some parts of the ocean because of certain responses, and 1% in others, because a lot of what the ocean does is just recycle the carbon.
Yeah, what I was sort of proposing was that we really need to study the marine microbiome and understand what a healthy microbiome is. Just like we study, human microbiomes of the gut and skin and try to decide on what is a healthy microbiome and what are the good organisms, what are the bad organisms, and how do we affect them when we do fertilization. And then how do we fertilize in order to optimize the good versus the bad and attempt to maintain a healthy marine microbiome. That was kind of the point that I was going to make in this meeting tomorrow. And I think there's a big role for synthetic biology in that. And I think it's a very fundamental and basic question. What is a healthy ocean? How do you know you've hurt the ocean if you don't know what a healthy ocean is?
Yeah, I've seen papers, one recently of an MIT group, Stephanie Dukovich, I think, but she was a co-author. I don't think she was the lead author, but they're predicting large changes to ocean microbiology in the future, right? All of these stresses, temperature, acidity, nutrient mixing. And the challenge though is, can we even measure that? And I think it's no was my answer. A lot of those shifts, we don't have the ability to make those types of continuous measurements. I can measure chlorophyll from space. I can't measure which plankton community, which microorganisms are there very well. I just have point measurements of that. So yeah, understanding that cycle, yes. We've convinced the Simons Foundation to fund some fundamental technology development so we could have autonomous vehicles that go around and sample that, what I'm calling the, everything from a 0.2 micron cell, but up through the food chain anyway, at the base of the food chain. So at least we could understand if it's changing and by why. I mean, that's the more important thing, but no, a good point. I like that idea. I'm gonna
Chris?
Cut this off at 6:30 my time. So we got about 8 minutes left. Is that okay, Claude?
Sure, that's fine. Chris, your question? Chris Harding, did you have a question? I think.
Hello.
Now we hear you.
Sorry about that. My microphone wasn't working. So I have a question, and my question is about the glacial rivers. I read recently that the glacial rivers can actually absorb or sequester as much carbon dioxide as Amazon rainforest. and they were talking about the temperature of the water as well as the sediment in the water. And this may be a little basic, but I was wondering if anybody's ever taken a look at the sediment, and is it in comparison, is it more absorption or more sequestering than what you see in the ocean on a regular basis, or is it less?
Boy, I'm just gonna plead my ignorance. I think, yeah, I mean, the land-based budget, the 1/3 includes, these are usually large-scale atmospheric towers and measurements that would include, I think, what's happening in areas, I hope, glacial rivers. Why a glacial river would be that more efficient? I don't think it would. It must be related to the alkalinity or some of the chemical that's, I mean, rivers are the way you get alkalinity, right? You weather rocks, you bring in those minerals. And so maybe that's the connection. Someone here might know more.
Well, I
about
can
that
jump in
study.
on that because glacial rivers don't support any life because there's so much sediment in them. They look like they can look like milk flowing into the ocean, and that's just a tremendous amount of very fine eroded rock. So that is a tremendous amount of alkalinity going into the ocean.
And that would, for the ocean, that type of process is geological time scales, right? Doesn't immediately have an alkalinity effect necessarily, might have in the estuary, but a lot of those things are longer time scales. So the people who talk ocean alkalinity, they point to weathering as being their model, a natural way to do this. What their challenge engineering wise is how to speed up that geological process and get things back in solution phase without causing other harm when you start introducing ground up minerals on large scales. Interesting stuff.
Okay, Neil, we'll give you another chance. You promised to be a good boy.
Okay, let me try this one then. I'm assuming that putting carbon into the ocean, keeping carbon in the ocean, isn't really the goal of all this. The goal of all this is to somehow or another, change or stabilize the climate of the planet. That's really what this whole exercise is about. And it's not a local exercise. It's not a US-based exercise. The effects would be global as far as the climate goes, although perhaps the effects, whatever they might be, of what you're doing in the ocean, if you're not doing it globally, could be more localized. So the question is, does doing any of this require some sort of global consensus? Is there agreement by everybody whether the climate should be warmer or cooler, whether we should make certain trade-offs in the ocean's biology and chemistry in return for this climate change? Is one of the risks in your calculation of unintended consequences a risk of inducing a war?
Yeah, the first part of that I agree with completely, in that the consequences that, if you call them negative, might be localized to where you do whatever these activities are. And the benefits, if we think of climate stabilization, the benefit would be global. And that is one of the issues of, I don't want to remove carbon or nutrients somewhere and cause an effect downstream like fisheries go bad, that type of thing. But that's what we need more data on, is we know we can all, people can run models. I'm not a modeler. And you can make some predictions. I think partly going forward, that chapter about governance and regulations is really important. Social licenses, who benefits, because also in that scenario of a local negative effect, someone might be making money off that, selling carbon credits, and then someone else might be being harmed because their fisheries decline because of what someone did upstream, that type of thing. So yes, it's a very serious issue in terms of how you move forward, whether as governments, as policy, or just trying to put down the next commercial company that says, we're going to do this and sell you credits on a voluntary market even, and someone comes after you for the damages that you've caused to them. we're not there yet. I think when we get there, we should be coming up with things like the London Convention, international protocols. If we're going to have, we need agreement precisely to deal with this kind of transboundary issue. Who benefits, who profits? Should governments do this? Should commercial companies do this? I think there's a lot of people that think it would only happen at scale if it was a profit motive behind this, and that might be true. Then you can get people coming out versus like which government would be in charge. I think it would take a scale of international effort, at least in terms of CDR, beyond solar radiation. You could take with one country and maybe create a very big global effect. I think everything I've talked about to have these global effects would take a lot of coordination and people and agreement on how to use the ocean commons, which is a bit of a challenge. We don't do that very well, right? We're more likely to cause wars and other things.
Okay, last question, Dave Herman.
Yeah, thank you, Claude, and I hope you don't mind. Can I just remark on something that was the key thing that I remember from the conclusion of the conference you hosted back in whenever it was, 14, 15 years ago. It was all, there was somebody at the end, and I don't remember who it was, and I think you included this in your summary. Somebody said that, the reason that we need to do the research now and start the research and also work on the global governance for, not just ocean iron fertilization, but any kind of geoengineering, is because you don't want somebody going rogue, like in the future. And, this is a worst case scenario, but hypothetically, there could be a country, say a Himalayan, a country that depends on Himalayan glacier water or something. And, 20, 30 years in the future, their climate has been affected so severely that they feel desperate and they have to do something severe. And then they just go off on their own and do some solar radiation management for their own individual benefit or that country's benefit, which drastically adversely affects their neighbors or other countries in other parts of the globe. And, as somebody just mentioned, that could spark a war, or at least, a lot of conflict. And that's what you want to prevent. And that's why, the prudent thing to do is to do the research now and to set up global governance systems to manage that research and also the eventual implementation of some of these strategies. So, and anyway, thank you for giving me a soapbox on that.
No, I agree with that.
Ken, thank you very, very much, both for your presentation and for allowing this extensive question and answer period. I have a feeling that somehow in some of our announcements, the times may have gotten messed up because I see some people on the West Coast coming on just now. But we will be posting this webinar on the alumni site. I understand it takes about 2 weeks. And I look forward to finding out much more about the oceans, not only their ability to sequester CO2, but our ability to keep them productive. 20% of the world's population depends on the ocean for their food source. So let's hope we can save our atmosphere and save our oceans.
Thanks for joining us. And for more information on how to connect with the MIT Alumni Association, please visit our website.